Module 6, Lecture B, Transfer Learning. By the end of this lecture, you will be able to load and adapt pre-trained CNN backbones from tf.keras.applications for new classification tasks, configure layer freezing and unfreezing strategies to balance feature reuse and task-specific learning, and implement a staged training schedule for fine-tuning and evaluate its impact on performance. Working with pre-trained models using tf.keras.applications. Pre-trained convolutional neural networks are usually accessed through model constructors that provide standard architectures and learned weights, such as VGG or ResNet trained on large image datasets. Using these models gives you a network that already recognizes basic visual features, like edges and shapes, which speeds up development. You can then adapt this pre-trained network to your specific task, such as classifying plant diseases from leaf images, instead of training a new model from scratch. When using pre-trained models, you must choose whether to load their existing weights or start from scratch, and whether to keep the original classification head or only the convolutional base. In transfer learning, you usually load the pre-trained weights but remove the original classification layers, since they are tailored to the model's original categories. This leaves you with a backbone that produces high-level features, onto which you can add your own custom layers for tasks like classification or detection. For instance, in medical imaging, you might keep the convolutional backbone and attach new dense layers to classify X-ray images while leaving the rest of the architecture unchanged. Pre-trained model builders fit naturally into your modeling workflow by letting you use a pre-trained backbone as just another component. You can wrap it in functional or sequential models, add new layers on top, and choose which parts to train or keep fixed. This modular design lets you build complex architectures without re-implementing low-level details. For example, you might plug a pre-trained backbone into a wildlife monitoring system for feature extraction, then add outputs for species classification and behavior recognition. Overall, this approach speeds up experimentation and iteration through simple, high-level constructor calls. Python code using tf.keras.applications. This script demonstrates a simple example of transfer learning using pre-trained models from the TensorFlow Keras applications module. It is designed to be accessible for beginners, with each step kept small and easy to follow. Overall, it introduces the basic idea of reusing existing trained models to build new solutions. The line starting with an exclamation mark is a shell command that installs TensorFlow version 2.20.0. Specifying this exact version makes sure the code runs with the expected TensorFlow features and behavior. This is important for compatibility with the rest of the project and for reproducing the same results later. In many projects, it is standard practice to fix the library version in this way. We begin by importing a few standard libraries that our script will rely on. The operating system library lets us work with files and directories on the computer. The random library is used to generate random numbers, which is important for tasks like setting a seed so results can be reproduced. Finally, the numerical computing library provides efficient tools for working with arrays and performing mathematical operations. We begin by importing TensorFlow, a main library used for machine learning and deep learning. Then we import Keras, a high-level interface within TensorFlow that makes it easier to build and train neural networks. Finally, we bring in the layers tools from Keras, which provide the basic components for creating network architectures. These imports prepare the environment so we can efficiently create and manage deep learning models. To make our code produce the same results every time it runs, we set a seed value of 42 for all the random number generators we use. We apply the seed to Python's built-in random module, to NumPy's random generator, and to TensorFlow's random generator. Using the same seed across these libraries ensures that any random operations behave consistently on each run. This reproducibility is important for running experiments and for debugging models reliably. We begin by printing the TensorFlow version used in the script so we can confirm which release is running. This quick check is important because different versions may offer different features or behave differently. Knowing the exact version helps with compatibility, troubleshooting, and reproducing results. By reading the version information at the start, we can more easily debug issues that might arise later. We start by loading the CIFAR10 dataset using the Keras datasets module. CIFAR10 is a standard machine learning benchmark with 60,000 images divided into 10 classes. The data is split into 50,000 training images and 10,000 testing images, each paired with a class label. These labeled images provide the supervised learning data needed to train our model and then evaluate how well it performs. For a quick demonstration, we work with a smaller subset of the data instead of the full dataset. We choose 1,000 samples for training and 200 samples for testing. We then take only the first 1,000 training examples and their corresponding labels. This reduced dataset lowers the computational cost and makes the demonstration run faster, while still showing the overall process. To keep the evaluation fast, the code uses only a small subset of the test data. Instead of running on the entire test set, it selects the first 200 test images and their labels. This reduced sample is enough to check performance while significantly cutting down the runtime. As a result, the evaluation becomes more efficient without processing every test example. The training data is first converted to a floating point format to allow precise calculations. Then each pixel value is divided by 255 so that all values fall between 0 and 1. This normalization helps neural networks train more efficiently and with greater stability. The same conversion and normalization steps are applied to the test data so that both datasets are processed in a consistent way. We set the target image size for the backbone model to a height and width of 96 pixels. This means all input images are resized to this fixed size. Doing so matches the input requirements of the pre-trained model we use and keeps the data consistent. This consistency is important for the model to work correctly with its existing architecture. We first resize all training images so they match the input size expected by the neural network backbone. Using TensorFlow's image resizing, each training image is adjusted to a height and width of 96 pixels. We apply the same resizing to the test images. This consistent size ensures the images are compatible with the MobileNet v2 model, which requires inputs of a specific shape for proper performance. We check the shape of the resized training data to confirm that all images match the new dimensions expected by the model. We do the same for the resized test data to verify its size. These simple checks are important before building the model because they help prevent input size mismatches that could cause errors during training or evaluation. We first define how many target classes our classification task has. For the CIFAR10 dataset, there are 10 distinct classes. So we set the number of classes to 10. This value is then used to configure the output layer of our neural network, so it has exactly 10 neurons. Each neuron corresponds to one class, allowing the model to classify each image into one of these 10 categories. We begin by defining an input layer in Keras that accepts images resized to 96 by 96 pixels. Each image has 3 color channels for red, green, and blue. This configuration ensures that the input data has the correct shape and format for the rest of the neural network. It is especially important when using a pre-trained backbone such as MobileNet V2, which expects inputs in this specific structure. To prepare data for MobileNet V2, we first use the dedicated preprocessing function provided by Keras applications, so the inputs match what the model expects. We then connect this function to the input layer through a lambda layer. This setup automatically preprocesses every input image before it enters the model. As a result, the data is handled in a way that is consistent with how MobileNet V2 was originally trained. We load the MobileNet V2 model from Keras applications and use it as a backbone for feature extraction. The input shape is set to match our resized images, which are 96 by 96 pixels with 3 color channels. We turn off the original top classification layers so we can add our own custom layers later. The model uses pre-trained ImageNet weights, giving us a strong starting point for transfer learning based on a large, diverse dataset. We set the backbone model to be non-trainable, so its weights are frozen and not updated during the initial training. This means only the new layers we add on top will learn from the data. By doing this, we keep the useful pre-trained features in the backbone while adapting the new layers to our specific task. This strategy is a standard part of transfer learning, where we reuse learned features instead of retraining the entire model from scratch. We feed the pre-processed images into the MobileNet V2 backbone to extract high-level visual features using its pre-trained layers. During this forward pass, we keep training turned off, so the backbone's weights do not change. This preserves the original pre-trained parameters while still allowing us to use the model's feature extraction capabilities. We use global average pooling to compress the feature maps produced by the backbone model. This operation replaces each feature map with a single value obtained by averaging all its elements. The result is a compact feature representation that reduces dimensionality while keeping important information. This streamlined output is then well suited for input to the following dense layers in the model. We now add a dense layer with 64 units that uses the ReLU activation function. This activation introduces nonlinearity, which helps the model learn more complex patterns in the data. The dense layer refines and strengthens the features produced by the earlier layers. It prepares these features so they can be effectively used in the final classification step. We finish the model by adding a final dense layer that acts as the classifier for the CIFAR-10 dataset. This layer has 10 units, one for each class in the dataset. It uses the softmax activation function, which turns the raw outputs into a probability distribution over the 10 classes. This makes it suitable for multi-class classification, since the model's output directly represents the predicted probabilities for each class. We now build the full transfer learning model in Keras by defining a single model object. This model takes the resized images as inputs and produces the final classification predictions as outputs. In doing so, it connects the input layer through all the intermediate layers we set up, including the MobileNet V2 backbone and the dense layers, to the output layer. The result is one cohesive model that is ready to be trained on our task. To compile the model, we choose the main training components, the optimizer, loss function, and evaluation metric. We use the Atom optimizer with a learning rate of 0.001, which adjusts the learning rate automatically during training. For the loss, we select sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. We also track accuracy as the key metric to measure how well the model performs during both training and testing. We start training by updating only the new classification head while keeping the pre-trained backbone frozen, so we can use its existing features without changing them. The model is trained on the resized training images and their labels for 2 epochs, meaning it passes over the entire training set twice. We use a batch size of 32 samples per update and reserve 20% of the training data for validation to monitor performance during training. The training progress output is turned off to keep the console output clean. We evaluate the model with its backbone kept frozen by running it on a small subset of test images and their labels. An evaluation function processes these inputs and computes how well the model performs. The evaluation runs silently without showing progress. It returns 2 key metrics, the loss and the accuracy on the test data. These values tell us how the model is performing before we apply any fine-tuning. To fine-tune the model, we unfreeze some of the deeper layers in the MobileNet v2 backbone so they can be updated during training. Specifically, we take the last 20 layers of the base model and set them to be trainable. This allows these layers to adjust their weights based on our data, helping the model better adapt to the specific characteristics of our dataset. We recompile the model with a lower learning rate to make fine-tuning safer and more stable. Specifically, we use the Atom optimizer with a learning rate of 0.0001. The loss function stays as sparse categorical cross-entropy, which is appropriate for multi-class classification. We also continue to track accuracy as the main metric to monitor performance during training and evaluation. We now fine-tune the model with some layers unfrozen by training it once over the resized training data and labels. The model processes the data in batches of 32 samples, updating its weights after each batch. During training, 20% of the training data is held out to check how well the model is performing. The training progress details are turned off, so no updates are printed while it runs. Next, we evaluate the fine-tuned model using the test subset. We run it on the resized test images and their labels to measure how well it performs. The evaluation returns the loss, which reflects how closely the predictions match the true labels, and the accuracy, which is the proportion of correct predictions. The detailed output is turned off so the process stays quiet and we can focus only on these final metrics. We first report the model's accuracy with the backbone frozen to establish a baseline before any fine-tuning. Then we compare this to the accuracy after fine-tuning, when some backbone layers are allowed to be trainable, to see how much performance improves. Finally, we count and report how many backbone layers are trainable, which shows how much of the model was actually adjusted during fine-tuning. This script demonstrates transfer learning with TensorFlow by using a pre-trained MobileNet v2 model on a small subset of the Cipher-10 dataset. The images are resized to match the model's input, and at first, only a new classification head is trained, while the backbone's weights remain frozen. After a short initial training and evaluation, the script then unfreezes the last 20 layers of the backbone and fine-tunes them with a lower learning rate. A second evaluation shows improved accuracy, and the script finishes by reporting how many layers in the backbone are now trainable, illustrating how fine-tuning can boost model performance. Input preprocessing essentials. When using pre-trained convolutional networks, you must format your input images to match what the original model expects. This includes using the correct image size, the right order of color channels, and the proper pixel value scaling. If these differ from the training setup, the learned features may not line up, and performance can drop. For example, using rectangular instead of square images can distort objects, and mixing up color channels can mislead the model, especially in color-sensitive tasks like traffic sign recognition. When using pre-trained models, it is essential to match the pixel value ranges and normalization they were trained with. Some models expect pixel values between 0 and 1, while others expect values centered around 0, using the original dataset's mean and standard deviation. If you ignore these expectations, the activations inside the network can become too extreme and lead to unreliable predictions. For example, a model trained on bright, normalized images may misclassify darker, unnormalized images because their brightness and contrast do not match. Proper normalization keeps your input images consistent with the training data, so the model's filters work as intended. When adapting a pre-trained model to a new task, you should match your preprocessing as closely as possible to the original model setup, while making only careful, domain-specific adjustments, such as contrast enhancement or denoising. These transformations must be consistent and should not break the assumptions the model was trained on, for example, by keeping brightness, color, and normalization similar to the original data. It is essential to apply the same preprocessing steps during training, validation, and deployment, so the model sees data in a consistent way. Treat preprocessing as a core part of the end-to-end pipeline to help the model transfer its learned knowledge effectively to the new task. Python code, input preprocessing essentials. This script introduces the basics of input preprocessing for images. It compares using raw image data with using preprocessing that is tailored to a specific model. The goal is to show beginner-friendly workflows for handling vision data in TensorFlow, so you can prepare images correctly before training or inference. The commented line recommends installing TensorFlow version 2.20.0 to match the version expected by the script. Using this specific version helps ensure that all required features and behaviors work as intended. Specifying an exact library version is a common way to avoid problems that can arise when newer releases introduce changes. We begin by importing 3 key tools for our script. The operating system module lets us work with files and environment settings. NumPy provides efficient support for arrays and numerical calculations. TensorFlow offers functions for building and training neural networks. Together, these imports prepare the environment so we can handle data and models effectively throughout the rest of the program. We begin by setting fixed random seeds in tools like NumPy and TensorFlow so that any random operations produce the same results every time the script runs. This makes our experiments reproducible, which is especially important when debugging or comparing different runs. By controlling the random number generation, we ensure consistent behavior and maintain the integrity of our experimental results. This line displays the version of TensorFlow currently in use. It provides a quick check that your environment is using the expected version of the library. Confirming the version helps ensure that your code is compatible with the installed TensorFlow setup. We begin by using MobileNet v2, a small pre-trained neural network from TensorFlow's Keras library, as the backbone for our image processing pipeline. This model is commonly used for image classification tasks and provides a strong starting point without training from scratch. We then apply a preprocessing function designed specifically for MobileNet v2, which adjusts the images so they match the model's expected input format and scale. This preparation ensures the images are correctly formatted for accurate and efficient training or inference. We use the CFAR10 dataset from the Keras datasets module in TensorFlow, which contains small images grouped into 10 categories and is well-suited for simple image processing tasks. The loading function returns separate training and testing sets, but in this case, we only work with the training portion. The training images are stored in one variable and their corresponding class labels in another. This setup gives us a manageable dataset for demonstrating basic image preprocessing techniques. To keep experiments fast and manageable, we work with a small subset of the CFAR10 training data instead of the full dataset. Specifically, we select the first 8 training images along with their labels. Using this tiny sample lets us quickly test and iterate on preprocessing steps. It allows us to observe their effects without the time and computational cost of processing every image in the dataset. We check the shape of the original sample images to confirm they have the expected dimensions. This verification step ensures the data is in the correct format before we continue. By confirming the image sizes early, we avoid problems in later processing or transformations that rely on consistent input dimensions. We set the target image size to a height and width of 224 pixels because this is the input resolution expected by the MobileNet V2 model. Resizing all images to these dimensions ensures they are compatible with the model's architecture. Meeting these input requirements is important for the model to process the images correctly and make accurate predictions. We use a resizing layer from TensorFlow to adjust all input images to a specific height and width, defined earlier in the script. This step is essential because MobileNet V2 expects images of a fixed size. By standardizing the image dimensions, we ensure that preprocessing is consistent and that the model receives inputs in the correct format. This makes the overall workflow more reliable and easier to manage. The code changes the sample images to use the float32 data type. This format is commonly required by preprocessing steps and machine learning models. Using float32 keeps the data consistent and helps maintain numerical stability during calculations. The code resizes the sample images so they match the input size required by the MobileNet V2 model. It uses a TensorFlow resizing layer to set each image to a height and width of 224 pixels. This step is essential because the model only works correctly with inputs of this specific size. By resizing the images, we make them compatible with the pre-trained model's architecture and enable accurate processing and predictions. We check the shape of the resized sample images to confirm they match the expected dimensions before moving on. This verification step makes sure each image has been resized to the target size required by the model. Doing so maintains consistency across the data and helps prevent errors in later processing steps. We first examine the range of pixel values in the resized images before applying any normalization. By checking the minimum and maximum pixel values at this stage, we get a clear picture of the raw data characteristics. This initial step is important because it provides a baseline for later comparing how different preprocessing methods change the data. We next apply the MobileNet V2 specific preprocessing step to the resized images. This adjusts the pixel values so they match what the MobileNet V2 model expects as input. In practice, it scales and normalizes the pixels to the range used during the model's training. This ensures the images are in the correct format and helps the model perform as intended. After we apply the MobileNet V2 specific preprocessing to the resized images, we check the minimum and maximum pixel values. This shows how the preprocessing step has scaled and normalized the data to the range expected by the model. By verifying these values, we confirm that the images are correctly prepared and aligned with the input requirements of the MobileNet V2 architecture. We begin by creating a minimal model using a pre-trained backbone called MobileNet V2, which is commonly used for image classification. We turn off the original top classification layers so we can later add our own custom layers. We load weights that were trained on the ImageNet dataset to take advantage of features the model has already learned. Finally, we set the input size to images that are 224 by 224 pixels with 3 color channels, so the data matches what the model expects. The code sets the base model to be not trainable, which freezes all layers of the pre-trained backbone, so their weights are not updated during training. This is done to keep the backbone's learned features fixed, while we experiment with different pre-processing steps. By freezing the backbone, any change in performance can be attributed to the pre-processing adjustments, rather than to changes in the backbone's parameters. We build the model by first defining an input layer that matches the resized images, with a height and width of 224 and 3 color channels. These inputs are passed through the pre-trained MobileNet v2 backbone in inference mode, so its learned weights remain fixed. We then apply global average pooling to convert the backbone's feature maps into a single feature vector for each image. After that, we add a dense layer with 10 units and a softmax activation to produce class probabilities for the 10 CIFAR 10 categories. Finally, we connect the input layer, backbone, pooling, and classification head into one model that can be used for training or inference. A model is compiled with a simple setup. It uses the Atom optimizer, which is a common choice for efficiently training neural networks. The loss function is sparse categorical cross-entropy, appropriate for multi-class classification when the labels are given as integers. The model also tracks accuracy as a metric, so we can monitor how well it performs during training and evaluation. We run a forward pass of the model using images that have been correctly pre-processed to match the input format expected by the MobileNet v2 backbone. During this step, the model generates predictions for these adjusted images without showing any progress output. This process is essential for assessing how well the model performs when the input data is prepared according to its requirements. The code first normalizes the resized images by dividing each pixel value by 255, changing the range from 0 to 255 into a range between 0 and 1. This standard scaling step prepares the image data for the model. It then feeds these scaled images into the model to generate predictions, running quietly without extra output. This process is used to check how well the model performs when the images are only resized and scaled, without applying the special preprocessing normally expected by the MobileNet v2 model. We evaluate model confidence by first looking at images that were correctly preprocessed. For each image, we take the highest prediction score as the model's confidence, then average these scores to get a single confidence value. We repeat this process for images that were only resized and not fully preprocessed. Comparing these two average confidence values shows how much proper preprocessing affects the model's confidence in its predictions. The code compares the model's average confidence when using properly preprocessed images versus raw scaled images. It computes the mean confidence for each case and rounds the values for easier reading. By contrasting these two averages, it shows how correct processing can significantly affect how confident the model is in its predictions. The final line of the script reminds us that input data must match the size and normalization expected by the backbone model. A model's performance strongly depends on receiving data in the same format it was trained on. When we correctly resize and normalize input images, we align with the model's requirements. This alignment is essential for obtaining accurate and reliable predictions. This script shows how to properly preprocess image data for a MobileNet v2 model in TensorFlow. It loads a subset of the CIFAR 10 dataset, resizes the images to the model's required input size, and applies the specific preprocessing function that adjusts pixel values to the expected range. A simple classifier is built using MobileNet v2 as the feature extractor, followed by pooling and a dense output layer. The model's predictions are then compared on correctly preprocessed images versus only scaled raw images, and the average confidence is higher with the proper preprocessing. This demonstrates that matching the preprocessing steps to the model's expectations is crucial for achieving better performance. Selecting CNN backbones. Choosing a convolutional neural network backbone for transfer learning means deciding what kind of visual knowledge you want from a pre-trained model. Architectures such as VGG, ResNet, MobileNet, and EfficientNet differ in accuracy, speed, and memory use. Large, deep models capture more complex patterns but demand more computational resources, while smaller models are better suited for fast, real-time, or mobile applications. The main goal is to match the model's capacity and resource requirements with the needs and constraints of your specific task. When choosing a pre-trained model for your domain, focus on how well its learned features will transfer to your type of images. Most models are trained on general color images and learn basic patterns like edges and textures that often work well for many tasks, including medical and satellite imaging. However, if your data is very different, such as grayscale X-rays or multispectral images, some architectures will adapt better than others. In these cases, it is often effective to use backbones like ResNet or DenseNet, which handle texture and scale variations well and have proven stable and powerful in medical imaging. When choosing a convolutional neural network backbone, match its architecture to your training and deployment needs. ResNet, with its skip connections, tends to fine-tune reliably by keeping gradient flow stable in deep networks. MobileNet and EfficientNet use specialized convolutions and scaling to offer a good trade-off between accuracy and efficiency, which suits edge devices like drones or wearables. You should also consider the input image resolution, since some backbones are better for small images, while others handle high-resolution, detail-heavy tasks. By aligning these architectural properties with your data and hardware constraints, you can select a backbone that strengthens your transfer learning pipeline. Layer freezing techniques, controlling layer trainability. When using a pre-trained convolutional network, an important choice is which layers should keep their existing weights and which should be updated, a process called controlling layer trainability. The network acts as a hierarchy of feature detectors, where early layers learn simple patterns and deeper layers learn more complex, task-specific features. By deciding which layers to freeze and which to train, you control how much of this learned hierarchy you reuse and how much you adapt to your new task. For example, when adapting a model to classify industrial components, you might freeze most layers to preserve their general features and only train a small portion to capture patterns unique to those components. Controlling which layers of a neural network are trainable lets you manage both learning behavior and computational cost. Freezing layers saves memory and speeds up training because those layers keep their weights fixed, which is especially helpful with large models or limited hardware. In areas like medical imaging with little data, freezing layers preserve strong, general features learned from large datasets. You can then selectively unfreeze parts of the network to adapt it to a specific task, capturing new patterns while keeping the model's broad visual understanding. When deciding which layers of a neural network should be trainable, focus on how similar your new task is to the one the model was originally trained on, and how strong your dataset is. If the tasks are similar, you can freeze more layers and rely on existing learned features. If the tasks are quite different, such as moving from standard photos to satellite images, you should allow more layers to be trainable so the model can learn new features. Trainability is not all or nothing. You can selectively choose which parts of the network learn. This control lets you balance reusing existing features with adapting effectively to the new task. Python code, controlling layer trainability. This script demonstrates how to control whether layers in a neural network are trainable or not. It uses a small pre-trained backbone model as an example and focuses on freezing convolutional layers so their weights stay fixed during training. It also shows how to unfreeze those convolutional layers when you want to fine-tune them. Overall, the goal is to illustrate practical control over layer trainability in a pre-trained model. The line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0, not a piece of Python code. It makes sure that this exact version of TensorFlow is available before the script runs. This matters because different TensorFlow versions can change features or behavior. Installing a specific version helps keep the code consistent and compatible. We start by importing 3 key libraries. The operating system library lets us interact with the system for tasks like working with files or environment variables. The random module provides tools to generate random numbers, which we can use for things like setting seeds to make results reproducible. Finally, the numerical computing library NumPy supports efficient array operations and helps us set deterministic seeds for our numerical work. We set deterministic seeds so our code produces the same random results every time it runs. First, we fix the seed in the random library, which makes all its random operations repeatable. Then we set the seed in NumPy's random generator to the same value, so its random numbers are also consistent. This practice is essential for reproducibility, especially when debugging or comparing how models perform across different runs. We begin by importing TensorFlow and its Keras modules, which provide the main tools we need for machine learning and deep learning. TensorFlow is the core library that handles complex computations, while Keras is a high-level interface that makes it easier to build and train neural networks. By bringing these into our project, we can efficiently construct, train, and manage our models using their built-in functions and utilities. We begin by printing the TensorFlow version in use to quickly confirm the environment is set up as expected. This simple check helps verify compatibility, since different versions can change features or behavior. It also makes debugging easier by clearly showing which version is running. Overall, it is a basic but important first step before working with TensorFlow. The code first asks TensorFlow which physical devices are available, and specifically checks for any GPUs. If at least one GPU is found, it sets the device type to GPU so computations can run faster on that hardware. If no GPU is available, it automatically falls back to using the CPU instead. This lets the script adapt to the current machine and use the best available resources without manual changes. The code checks whether a physical graphics processing unit is available, and then prints which type of device will be used to run the model. If a graphics processor is found, it selects that. Otherwise, it falls back to the central processing unit. This message helps you understand what kind of computational resource is being used for the model's execution. We start by loading the CFAR10 dataset using the Datasets module from Keras. CFAR10 is a standard machine learning benchmark with 60,000 color images grouped into 10 classes. It is already divided into 50,000 training images and 10,000 test images. This loading step sets up the data pipeline so we can train the model on the training set and evaluate its performance on the test set. The code prints the shapes of the training data and labels from the CFAR10 dataset to verify that everything has been loaded correctly. By checking these dimensions, you confirm that the data matches what you expect before doing any subsampling or further processing. This step helps ensure the dataset has the right format and size for the later stages of the script. To speed up training, we work with a smaller subset of the original training data. We choose a subset size of 2000, meaning we only use the first 2000 input samples and their corresponding labels from the full training set. By training on this reduced set, we can test ideas and iterate on our model more quickly without processing the entire dataset each time. The training data is first converted to floating point numbers. Then each pixel value is divided by 255, so that all values fall between 0 and 1. This normalization helps the model train more effectively because the input features share a similar scale. The same process is applied to the test data to keep the inputs consistent during both training and evaluation. The code first flattens the training labels, turning a two-dimensional array into a one-dimensional array so they are easier to use during model training. It then applies the same flattening to the test labels. This makes both sets of labels consistent and in the format that many machine learning models expect. Having labels in a flat, one-dimensional form is important for proper processing and training. We define the input shape of our model as a tuple with three values, 32, 32, and 3. This means each input image is 32 by 32 pixels, with 3 color channels, usually red, green, and blue. Specifying this input shape is essential because it tells the model exactly what size and type of data to expect. It also guides how the layers of the network are built and how the data will move through the model. We begin by defining an input layer for our model using Keras. This layer specifies the shape of the data the model will receive, which here is a three-dimensional image with a height and width of 32 pixels and 3 color channels. The input layer acts as the entry point of the model and establishes the structure on which all later layers are built. We add a convolutional layer to the model that uses 32 small 3x3 filters with a ReLU activation function. Pause. This layer takes the backbone input image and automatically learns useful visual features. By sliding the filters across the image, it captures important spatial patterns such as edges and textures. This helps the model build a hierarchy of features that are useful for later stages of processing. Next, we add a second convolutional layer to the model that uses 64 small 3x3 filters with a ReLU activation. This new layer takes the output from the first convolutional layer and processes it further. By increasing the depth of the network in this way, the model can learn more complex and detailed features from the data. We now apply a max pooling layer to the model's current output. This layer scans each 2x2 block of pixels in the feature maps and keeps only the maximum value. By doing this, it reduces the spatial dimensions, which lowers computational cost and helps the network focus on the most important features. This downsampling step is a key part of efficient processing in convolutional neural networks. We now add another convolutional block to the model, using a two-dimensional convolution layer with 128 filters of size 3x3. This layer applies the ReLU activation function to introduce nonlinearity. It takes the output from the previous layer and processes it further, increasing the depth of the feature maps. As a result, the model can learn more complex patterns in the data. In this step, we apply global average pooling to the output of the previous layer. This operation takes each feature map and replaces it with a single value obtained by averaging all its elements. As a result, the spatial dimensions are condensed into one compact feature vector. This reduces model complexity and conveniently prepares the features for connection to fully connected layers used for classification. We are building a backbone model in Keras by taking the previously defined input layer and passing it through a series of convolution and pooling layers that extract meaningful features from the data. These feature extraction layers are then wrapped into a single Keras model object, which we name toy backbone, to indicate that it is a simplified, pre-trained style structure. This backbone will later be plugged into a larger model, where it serves as the feature extractor. At that stage, we can choose whether its layers are trainable or frozen in order to control how much we fine-tune the model's performance. We treat the backbone model as already pre-trained and want to keep its learned features unchanged at first. To do this, we go through each layer in the backbone and mark it as not trainable. This freezes the layers so their weights are not updated during training. With the backbone fixed, we can focus on training only the new layers added on top, while still benefiting from the existing learned features. To find out how many layers in the backbone model are still trainable, we sum the trainable flag for each layer using a numerical tool like NumPy. This gives us the total number of layers whose weights can be updated during training. We then print this number to confirm how many layers remain trainable after freezing the backbone. This check helps verify that the freezing step was applied correctly. We begin by adding a new input layer for the classification head of our model. This layer is configured to receive images with the same dimensions as those in the CFAR10 dataset, which are 32 by 32 pixels with 3 color channels. It acts as the entry point for images into the classification head, so they can be passed through and processed by the rest of the model. We pass the input images through a backbone model that is kept fixed during training, meaning its weights are not updated. In this setup, the backbone serves purely as a feature extractor. It produces stable, consistent feature representations, and only the classification head learns and updates its parameters based on these features. We build the classification head by first adding a dense layer with 64 units and a ReLU activation, which compresses the features from the backbone into a more useful representation. Then we add a second dense layer with 10 units and a softmax activation. This final layer produces the class probabilities for the 10 categories in the CFAR10 dataset. We build the complete transfer learning model using the Keras model class, connecting the head input layer to the final dense layer that produces the classification outputs. We give this combined model the name transfer model. This design links the frozen backbone to the new classification head so that we can apply transfer learning effectively on the CFAR10 dataset. To begin training the model, we compile it by choosing an optimizer, a loss function, and an evaluation metric. We use the Atom optimizer with a learning rate of 0.001, which is a standard choice because it adapts the learning rate during training. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. We also track accuracy as the main metric to evaluate how well the model performs during both training and testing. We start training by updating only the new classification head while keeping the backbone of the model frozen. Using the Keras training routine, we train on a small subset of CFAR10 images and their labels for 2 epochs, so the model sees the entire subset twice. The batch size is set to 64, meaning the model updates its weights after every 64 samples. Training runs silently with no progress output, and 10% of the training data is held out to monitor validation performance during training. We now evaluate the model while its backbone remains frozen. Using the model's evaluation function, we test it on the first 1,000 samples from the test set. This evaluation returns 2 key metrics, loss and accuracy. These values show how well the model performs with its frozen layers. The evaluation is run in a quiet mode so that only the final results are reported without extra detailed output. To begin fine-tuning the model, we unfreeze the last few layers of the backbone so they can be trained. Specifically, we make the final 3 layers trainable, which allows their weights to be updated during training. This adjustment lets the model adapt more closely to the new dataset and better capture its specific patterns. We now recompile the model with a lower learning rate because we have unfrozen some layers and want to fine-tune them more gently. We use the Atom optimizer for its adaptive learning rate behavior and set the learning rate to 1 × 10⁻⁴, which is smaller than before to allow more precise updates. The loss function remains sparse categorical cross-entropy, which is appropriate for classification with integer labels, and we continue to track accuracy to monitor model performance during training. We now retrain the model with some backbone layers unfrozen so they can be updated. Using the smaller training dataset and labels, we run training for 2 epochs, meaning the model sees the entire dataset twice. The batch size is set to 64 samples per update, and training runs silently, with no progress output. We also reserve 10% of the training data for validation to monitor the model's performance during training. After unfreezing some layers of the model, we evaluate its performance to see how much the accuracy has improved. We do this by running the model's evaluate function on a subset of the test data, using only the first 1,000 samples. This evaluation returns the loss and accuracy values for that portion of the data. We also turn off detailed output during this step, so we can focus directly on the final performance metrics. We first report the model's accuracy with the backbone frozen to establish a baseline for comparison. Then we measure accuracy again after unfreezing the last convolutional block to see how fine-tuning changes performance. Finally, we output how many layers are now trainable to confirm that the intended parts of the model are actually being updated during training. This script shows how to control which layers of a neural network are trainable in TensorFlow and Keras. It first builds a simple convolutional backbone that imitates a pre-trained model, freezes all its layers, adds a new classification head, and trains only this head on a small subset of the CFAR10 dataset. The model is evaluated to measure accuracy with the backbone frozen. Then the last convolutional block of the backbone is unfrozen. The model is recompiled with a lower learning rate and trained again. A final evaluation compares accuracy before and after fine-tuning, demonstrating that unfreezing and training selected layers can improve model performance. Training classifier head only. When adapting a pre-trained convolutional network to a new task, a common approach is to freeze the convolutional backbone and train only a new classifier head. In this setup, the backbone serves as a fixed feature extractor, while the newly initialized head learns to map those features to the specific classes of the new problem. This strategy greatly reduces the number of trainable parameters, making training faster and less prone to overfitting, which is especially helpful when you have limited data. When adapting a pre-trained network to a new but similar task, a simple and effective approach is to freeze the backbone and train only the classifier head. The frozen backbone still recognizes common visual patterns, while the new head quickly learns the new labels. This usually gives strong performance with little training time and serves as a solid starting point for any later fine-tuning of the whole model. Training only the classifier head while keeping the backbone fixed can reduce overfitting, especially when data is limited or noisy. The frozen backbone prevents the model from memorizing dataset quirks and instead relies on general patterns it has already learned, which is useful in areas like industrial inspection or rare disease diagnosis. However, if the new task is very different from what the backbone was originally trained on, these fixed features may not be sufficient and performance can plateau. In that case, starting with a frozen backbone and then gradually fine-tuning deeper layers can provide a strong initial baseline while still allowing better adaptation later. Python code. Training classifier head only. This script focuses on training only the classifier head of a model. It keeps a pre-trained backbone frozen and updates only the top layers. This approach is an example of a conservative transfer learning strategy, where most of the model is reused as is, and only the final classification part is trained for the new task. The line that starts with an exclamation mark is a command to install TensorFlow version 2.20.0. It is usually run in a Jupyter notebook or a similar environment that can execute shell commands. This ensures that the script uses that exact TensorFlow version, which is important because different versions can have different features and compatibility. We begin by importing a few key libraries needed for our work. The operating system library lets us manage files and directories, while the random library helps us generate random values for more varied data handling. We then use NumPy for efficient numerical computations with arrays. Finally, we import TensorFlow, which provides the tools to build and train machine learning models, and will be central to training our classifier head. We set a seed value, such as 42, so that all random operations in our code give the same results every time, which is important for reproducible experiments. We first set the seed for the standard random library so its random numbers are consistent. Then we set the seed for the NumPy random number generator, which controls randomness in NumPy operations. Finally, we set the seed for TensorFlow's random number generator, affecting things like how neural network weights are initialized. Using the same seed across these libraries makes the overall behavior of our experiments deterministic. We check which version of TensorFlow is being used by reading its version attribute. This tells us exactly which release is running in our environment. Knowing the version helps us confirm compatibility and understand which features and behaviors are available in that specific setup. The code first checks whether any graphics processing units are available using TensorFlow's configuration tools. If it finds at least one, it chooses the graphics processor so the program can run faster. If no graphics processors are found, it falls back to using the central processing unit instead. This setup lets the code automatically adapt to the available hardware to improve speed and efficiency. This line displays whether computations will run on a graphics processor or on the main processor. It relies on a previously set variable that checks if a graphics processor is available. Knowing which type of hardware is being used helps you understand the environment where the model will run. This can influence both performance and how computing resources are managed. We use Keras tools to load the CIFAR-10 dataset, a standard benchmark in machine learning with 60,000 small color images divided into 10 classes. The data is split into 50,000 training images and 10,000 testing images, so we can both train and evaluate our model. Each image is 32 by 32 pixels with 3 color channels, and each label is an integer that indicates the class. This structure provides a clear and consistent setup for building and assessing image classification models. The code converts the pixel values in the training and test images from integers to floating point numbers and scales them to a range from 0 to 1. It does this by dividing each pixel value by 255, which is the maximum value in an 8-bit image. This normalization step ensures that all input data is on a consistent scale, which helps improve the stability and performance of the model during training. To make the demonstration faster, we work with a smaller subset of the data. We limit the training set to 2,000 samples and the test set to 500 samples. We do this by taking the first 2,000 entries from the original training data and their corresponding labels. Using this reduced dataset keeps the process manageable and speeds up training while still illustrating the main ideas. To speed up evaluation during development, we create a smaller subset of the test data by selecting only a portion of the test images and their labels. This allows us to run quick checks when testing changes or debugging, instead of using the full test set every time. The subset is formed by taking the first group of samples from the original test set, based on a predefined number of test examples we want to include. The code first prints the shape of the training subset to confirm that its dimensions match what we expect, which helps avoid broadcasting errors during later operations. It then prints the shape of the test subset for the same reason, checking that this data is also correctly structured. Verifying these shapes is an important debugging step that confirms the preprocessing has been applied properly before moving on to further processing or model evaluation. We set the image size to 96 by 96 pixels so it matches the input expected by the MobileNet v2 model, ensuring each image is resized correctly for the network. We also define the number of output classes as 10, which corresponds to the 10 categories in the CIFAR10 dataset. With these settings, the model is configured to take properly sized images and classify each one into one of the 10 CIFAR10 classes. We begin by creating a resizing layer in TensorFlow that sets the target image height and width, and this layer automatically adjusts image dimensions. We then apply this layer to the small training dataset, so every image is resized to the chosen size. The same resizing is applied to the small test dataset to keep both sets consistent. This uniform image size is essential, so the data matches the input requirements of the MobileNet v2 model used later. We print the shape of the resized training data to verify that the resizing worked correctly and that the data now has the expected format. This quick check confirms that the input dimensions match what the model architecture requires. By doing this before building and training the model, we help prevent dimension mismatches and related errors during training. We begin by building a base model using MobileNet v2, a widely used convolutional neural network. The input is set to images that are 96 by 96 pixels with 3 color channels. We exclude the final fully connected layers so that MobileNet v2 serves only as a feature extractor. Its weights are initialized with pre-trained values from the ImageNet dataset, allowing us to take advantage of features learned from a large and diverse collection of images. In this step, we go through each layer of the MobileNet v2 backbone and mark it as not trainable, which freezes its weights so they are not updated during training. This turns the backbone into a fixed feature extractor that relies on its pre-trained knowledge. As a result, only the new classifier head is trained, while the backbone remains stable and efficient. This setup is a common strategy in transfer learning. The code reports how many layers in the MobileNet v2 backbone are frozen, meaning their weights will not be updated during training. This check confirms that the backbone is used only as a fixed feature extractor. By verifying the number of layers in the base model, we ensure that all of them are frozen, which is essential for the transfer learning approach being applied. We begin by defining an input layer for the neural network that is set up to receive images of a fixed size. Each image is resized to 96 by 96 pixels and includes 3 color channels. Using this specific shape ensures that all input images match the model's expected dimensions. This consistency allows the network to process the images correctly as they move through the layers. We first preprocess the input images using the procedure designed for MobileNet v2. This step adjusts the pixel values into the format that MobileNet v2 expects. By doing this, we ensure the images are correctly prepared so the pre-trained MobileNet v2 backbone can extract meaningful features from them. The pre-processed images are fed into a MobileNet v2 backbone that has been pre-trained on the ImageNet dataset and is used only as a feature extractor. By setting the model to not train during this step, all backbone layers are frozen and their weights remain unchanged. This lets the system reuse the powerful features learned from ImageNet while training only the new classifier head on the current task. This step applies global average pooling to shrink the spatial dimensions of the feature maps into a single feature vector. It does this by summarizing each feature map into one value per channel, capturing the overall information from the entire map. In convolutional neural networks, this is a common way to condense learned features into a compact form. The resulting vector is then ready to be passed into the dense layers for classification. We add a dense layer at the end of the model to act as the classifier. This layer has one unit for each class, which is 10 in this example. It uses a softmax activation function to convert the pooled features into a set of probabilities. These probabilities indicate how likely the input belongs to each of the 10 classes and provide the final class prediction. We build the final model by connecting the frozen backbone to the classifier head using the TensorFlow model class, defining both the inputs and outputs. The input is the resized image, which passes through the backbone to extract features. These features are then fed into the dense layer that serves as the classifier head. The model's output is the set of predictions produced by this trained head based on the features from the backbone. To understand a model's size and what gets updated during training, we first count its trainable parameters by adding up the products of the dimensions of all tensors that can be learned. We then do the same for non-trainable parameters, summing the products of the dimensions of tensors that stay fixed, such as those in a frozen backbone. These two totals show how many parameters are being optimized versus how many remain constant. This helps us gauge the model's complexity and where the training effort is focused. We first print the number of trainable parameters in the classifier head to see how many weights will actually be updated during training. Then we print the number of non-trainable parameters in the frozen backbone to show which part of the model stays fixed. Comparing these two counts makes it clear how the work is divided between the frozen feature extractor and the trainable classifier head. We begin by compiling the model to prepare it for training. We choose the Atom optimizer with a learning rate of 0.001 to control how much the weights change at each step. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are integers. We also track accuracy as a metric, so we can monitor how well the model correctly classifies inputs into the predefined categories during training and testing. To train the classifier head, we call the model's fit method using the resized training images and their labels. We train for 3 epochs, so the model goes through the entire dataset 3 times. A batch size of 32 controls how many samples are used before updating the model's parameters. We also reserve 10% of the training data for validation to monitor performance during training, and we turn off detailed progress output by setting the verbosity to 0. To check how well the model performs, we run an evaluation on a small subset of test images and their labels. The model's evaluation function calculates the loss, which measures how far its predictions are from the true values, and the accuracy, which shows the proportion of correct predictions. The evaluation is run in silent mode, so it does not display progress messages. The resulting loss and accuracy values are then stored for later use or analysis. This script reports a brief summary of how the model performs on the test data using the frozen backbone. It first prints the test loss, which measures the model's error on the test set, rounded to 4 decimal places. It then prints the test accuracy, which shows how often the model's predictions are correct on the test data, also rounded to 4 decimal places. These rounded values make the evaluation results concise and easy to read. This script shows a conservative transfer learning setup, where only the classifier head is trained, while the pre-trained MobileNet v2 backbone stays frozen as a feature extractor. It loads and normalizes the CFAR10 images, resizes them to match the model's input size, and uses TensorFlow to handle the data and training. A new dense layer is added on top as the classifier, and the script sets deterministic seeds and checks for a GPU to ensure reproducible and efficient training. The model is compiled with the Atom Optimizer and sparse categorical cross-entropy loss, trained for 3 epochs on a small subset of the data, then evaluated on a test subset to report loss and accuracy. This approach quickly adapts the pre-trained model to a new task with minimal training by leveraging its existing learned features. Progressive layer unfreezing. Progressive layer unfreezing is a fine-tuning strategy where you gradually make more layers of a pre-trained network trainable instead of updating everything at once. You begin with most of the backbone frozen and train only the top layers or classifier head on the new dataset, so the model can adapt its decision boundaries while keeping its general features. After the classifier head stabilizes and performance stops improving significantly, you then unfreeze additional layers from the top down. This step-by-step approach helps protect useful learned features and makes optimization easier, especially when working with smaller or noisier datasets. In a convolutional network, different layers learn features at different levels of abstraction, so they should not all be fine-tuned equally when adapting to a new domain. Early layers capture basic visual elements like edges and textures that are broadly useful, while middle layers learn more specific patterns, and the deepest layers specialize in the original task's categories. Progressive unfreezing takes advantage of this by first adapting the layers closest to the output, then gradually allowing earlier layers to update only if needed. For example, when moving from everyday objects to industrial machinery, it may be enough to adjust only the top convolutional blocks, since the low-level feature detectors are still relevant, but the higher-level shapes must be adapted to the new context. When using progressive unfreezing, you gradually unfreeze deeper layers while lowering the learning rate, so pre-trained weights are updated gently. You could also use smaller learning rates for earlier layers and slightly larger ones for later layers. Throughout this process, you closely watch validation performance to see whether unfreezing more layers improves results or starts to cause overfitting. This helps you keep useful general features while adapting the model to your specific task and maintaining stable training. Python code, progressive layer unfreezing. This script shows how to progressively unfreeze layers in a neural network. It uses a small pre-trained convolutional network on CFAR10 images and focuses on controlling which backbone layers are frozen or trainable. The main idea is to start with most layers frozen, then gradually unfreeze deeper layers to fine-tune the model. This approach helps you understand and manage how much of the pre-trained backbone is updated during training. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. It forces the environment to use this exact version so the code runs with the correct setup. This is important for compatibility and for being able to reproduce results. The exclamation mark also shows that the command is intended for a Jupyter notebook or a similar tool that can run shell commands directly. We begin by importing a few key libraries needed for our work. The operating system library lets us interact with files and environment variables. The random library allows us to generate random numbers, which helps with setting seeds and making experiments reproducible. We then import NumPy for efficient numerical computations with arrays. Finally, we bring in TensorFlow, which we will use to build and train our neural network and apply progressive layer unfreezing. To make our results consistent and reproducible, we set a fixed seed value of 42 for all sources of randomness in our code. We first apply this seed to Python's random number generator, then to the random number generator in NumPy, and finally to TensorFlow's random number generator. TensorFlow relies on randomness for tasks like initializing neural network weights, so controlling its seed is especially important. By setting the same seed for each of these systems, we ensure that every run of the script produces the same outputs, which is essential for debugging and verifying experiments. We begin by printing the current TensorFlow version to understand the exact environment in which the code is running. This helps ensure compatibility, since different versions can have different features or behaviors. Knowing the version is also useful for debugging issues and for accurately reproducing results later on. The code first checks which physical devices are available for computation, focusing on whether any GPUs are present. It uses a TensorFlow configuration method to list all GPU devices, and if at least one is found, it reports that a GPU will be used. If no GPUs are detected, it falls back to using the CPU and prints a message to indicate this. This device check is important because running deep learning training and inference on a GPU can greatly improve performance compared to using only the CPU. We begin by loading the CIFAR10 dataset using the image datasets provided in TensorFlow's Keras module. CIFAR10 is a standard benchmark for image classification, with 60,000 images divided into 10 categories. The loading function returns separate training and testing sets, and each set contains images paired with their labels. This structure makes it straightforward to access, prepare, and use the data for both training a model and evaluating its performance. To speed up training and make experimentation easier, we use only a small subset of the CIFAR10 dataset. We choose 200 images with their labels from the training set and 100 from the test set. By working with just these first few samples, instead of the full dataset, we can train and evaluate our model much more quickly. This approach is especially useful for demonstrations and rapid testing. For evaluation, we use a small subset of the CIFAR10 test dataset. We simply take the first 100 test images along with their labels. This reduced set lets us quickly check how well the model performs. It provides a manageable way to assess accuracy without running on the full test dataset. To prepare the training images, they are first converted to floating point numbers so they work correctly with later computations. Each pixel value is then divided by 255, which rescales the data so all pixel values fall between 0 and 1. This normalization step is common in image processing and helps the model learn more effectively from the input data. The code first prints the shape of the training data, including both images and labels, to confirm that the data has been loaded and sliced correctly. Pause. It then prints the shape of the test data, again for both images and labels, to verify that the test subset is set up properly. Pause. Checking these shapes ensures that the data dimensions match expectations before moving on to building the model. We set the image size to 96 by 96 pixels. so that all inputs match the dimensions expected by the backbone model. This ensures images are resized correctly before entering the network. We also define the number of classes as 10, matching the 10 categories in the CIFAR-10 dataset. This allows the final layer of the model to produce one prediction score for each of the 10 classes. We use TensorFlow's resizing layer to make all images the same size before feeding them into the model. This layer adjusts each image to a height and width of 96 by 96 pixels. We apply it to both the training and test images so they are transformed to identical dimensions. Ensuring that all images share the same shape is essential for providing consistent input to the model. We print the shape of the resized training data to confirm that the resizing worked correctly and that the data has the expected format before training the model. We do the same for the resized test data to verify that it is also correctly prepared. This quick check helps ensure both datasets are properly structured and ready for the next steps in the process. We build a small pre-trained backbone model using the MobileNet v2 architecture from TensorFlow Keras. Its input shape matches our resized images, which are 96 by 96 pixels with 3 color channels. We load only the convolutional base and leave out the top classification layers so we can attach our own classifier later. The model uses weights pre-trained on the ImageNet dataset, giving us a strong starting point for transfer learning. At the start of training, all layers of the backbone model are frozen, meaning their weights are not updated. This keeps the pre-trained features intact, so they are not changed by the new training process. With the backbone fixed, only the new classifier layers learn and adapt to the specific dataset. This strategy lets the model use its existing knowledge while customizing just the final layers for the new task. We build the model by first defining an input layer that matches the size of the resized images. These inputs are then preprocessed using the MobileNet v2 preprocessing step, so they are in the format expected by the pre-trained base model. The preprocessed data is passed through the base model with training turned off, so its weights are not updated. We then apply global average pooling to compress each feature map into a single vector, and finally add a dense layer with a softmax activation to output class probabilities, forming the classifier head of the network. We now build the full transfer learning model by defining a new Keras model that takes the resized images as input and passes them through the network. The network uses the pre-trained backbone to extract useful features from each image. These features are then fed into the dense classifier layer, which produces predictions for the 10 target classes. In this way, we reuse the pre-trained feature extractor and focus training on the classifier head for our specific classification task. We begin by compiling the model so it is ready to train the classifier head. We use the Atom optimizer because it adapts the learning rate during training, starting with a value of 1 times 10 to the minus 3. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are integers. We also track accuracy as a metric, so we can monitor how well the model is learning to classify the images over time. We start by training only the classifier head, while keeping the pre-trained backbone layers frozen, using the standard training function from Keras. The model is trained on resized images, and their labels for 2 epochs, meaning it passes through the training set twice. A batch size of 32 controls how many samples are used before updating the model's parameters. A separate set of resized test images and labels is used for validation to monitor performance during training, and detailed training output is turned off. This setup lets the classifier learn initial patterns while preserving the pre-trained backbone, helping stabilize learning before any fine-tuning. After training the model's classifier head, we evaluate its performance on the test data by running the model's evaluation function on the resized test images and their labels. We turn off detailed output during this step so it runs quietly. The evaluation returns the loss and accuracy on the test set, which we store for later use. This tells us how well the classifier head performs before we apply any further fine-tuning. We now gradually unfreeze the top layers of the backbone model so they can be fine-tuned. To do this, we go through the last 20 layers of the base model and mark each one as trainable. Making these layers trainable allows their weights to be updated during training. This fine-tuning step helps the model better adapt to the specific characteristics of our dataset. We recompile the model for fine-tuning by using a lower learning rate so the weight updates are smaller and the risk of overfitting is reduced. The optimizer is Atom with a learning rate of 0.0001. We keep sparse categorical cross-entropy as the loss function because it is appropriate for this kind of multi-class classification task. We also track accuracy as the main metric to monitor how well the model learns during training. We now retrain the model with some backbone layers unfrozen so they can be fine-tuned. The training function is called with the resized training images and labels, using 2 epochs so the model passes over the data twice. A batch size of 32 controls how often the weights are updated. We also supply resized test images and labels as validation data to track performance on unseen examples during training. Training runs silently with no progress output, and this fine-tuning step can improve the model's accuracy by updating the newly unfrozen layers. After gradually unfreezing some of the backbone layers, the model is evaluated again using the resized test images and their labels. This evaluation measures how well the model performs on the test data. It returns 2 main results: the loss, which reflects the model's error, and the accuracy, which shows how often its predictions are correct. These values are stored for later analysis, and detailed output is turned off during this evaluation to keep the process quiet. The code first reports the accuracy after training only the classifier head, rounded to 4 decimal places, to establish a baseline performance. It then reports the accuracy again after fine-tuning the model with some backbone layers unfrozen, using the same rounding for consistency. Comparing these 2 accuracy values shows how much performance improves due to progressive unfreezing and fine-tuning. This script shows how to use progressive layer unfreezing with a pre-trained convolutional neural network on the CFAR10 dataset. It prepares a reproducible environment, loads a small subset of the data, and pre-processes the images to match the input format of a MobileNet v2 backbone. At first, all backbone layers are frozen, and only the classifier head is trained for a short period, after which the model's accuracy is measured. Then, the top 20 backbone layers are unfrozen, the learning rate is reduced, and the model is fine-tuned for a few more epochs. The script finishes by reporting accuracy after both training stages, illustrating how progressive unfreezing can improve performance. Staged fine-tuning. 2-stage training. In 2-stage training for convolutional neural networks, you first use a pre-trained backbone as a fixed feature extractor and train only the new classification head. This keeps the convolutional layer's useful features learned from large datasets like ImageNet, while the new dense layers adapt those features to your specific task. By initially updating just the top layers, you make optimization more stable, reduce the risk of forgetting good features, and adapt quickly with relatively little data and computation. After training the classification head, You enter a second stage where you unfreeze some backbone layers and train the whole model together. This step refines the internal features so they better match the new domain. For example, a model first trained on general objects may keep its early layers, while deeper layers are adjusted to capture domain-specific patterns, such as medical tissue details. This fine-tuning typically improves both accuracy and robustness beyond what training only the head can provide. Two-stage training is useful because it fits real project limits, like scarce labeled data and short training time. You first train only the classification head to quickly get a baseline that might already be good enough, saving effort and resources. If you need better performance, you then fine-tune more layers while closely tracking validation results to avoid overfitting. This staged process makes experiments clearer and helps you decide how much extra adaptation your specific application really requires. Python code, two-stage training. This script illustrates a simple two-stage training process using a small pre-trained convolutional neural network as the backbone. The focus is on demonstrating the training setup rather than exhaustive experimentation. To keep things efficient, the script is designed for short runtime and produces only minimal output. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Using this exact version makes sure the code has the right dependencies. It also helps prevent compatibility problems that might occur with other TensorFlow versions. We start by importing 3 key libraries. The operating system library lets us work with files and environment settings. The random library allows us to generate random numbers, which is useful for tasks like shuffling data. Finally, we import NumPy, a numerical computing library that helps us handle arrays and perform mathematical operations efficiently. We start by importing TensorFlow, a main library used to build and train machine learning models. Within TensorFlow, we use Keras, a higher-level interface that makes creating neural networks easier. From Keras, we bring in the layers tools, which let us define parts of the network, such as convolutional, pooling, and dense layers. Together, these imports provide the core components needed to construct and train our neural network efficiently. We begin by setting a seed value of 42, so that any random operations give the same results every time we run the code, which is important for reproducible experiments. To do this, we set the seed in the random library, then in NumPy, and finally in TensorFlow. Using the same seed across these libraries makes the behavior of our code deterministic and easier to compare and debug. We check which version of TensorFlow is being used by reading its version attribute. Doing this confirms the exact release we are working with. Knowing the version helps us ensure compatibility and understand which features are available in that specific setup. We start by checking whether any graphics processing units are available, using TensorFlow's configuration tools, which list all physical devices of type GPU. This tells us if we can use GPU hardware to speed up our computations. We then print how many GPUs were found to quickly see the resources available for training our model. We begin by loading the CFAR10 dataset using the Datasets module in Keras. CFAR10 is a standard machine learning benchmark with 60,000 images divided into 10 classes. The data is split into 50,000 training images and 10,000 testing images. Each image has a class label, which allows us to train a model on the training set and then evaluate its performance on the test set. To keep the demonstration simple and efficient, we work with a reduced version of the dataset. We use 2,000 samples for training and 1,000 samples for testing. This smaller dataset makes the process quicker and easier to manage while still clearly showing how the training procedure works. We begin by working with a smaller subset of the training data to make experiments faster and easier to demonstrate. Specifically, we take the first 2,000 training images, along with their labels. This reduces the overall dataset size while still keeping a sample that is representative of the original data. Using this subset allows for quicker testing without losing the main characteristics of the full training set. For this demonstration, we use a smaller portion of the test dataset by taking only the first 1,000 samples. This keeps the process quick and manageable while still providing meaningful results. We separate the images and their labels into different variables, and we choose this subset so that the test data size matches the subset used for training. The code prepares the training and test images by converting their pixel values to a float32 format and scaling them from the original range of 0 to 255 down to a range of 0 to 1. This process is called normalization. It ensures that all input data is on a consistent scale, which helps machine learning models train more effectively and with greater numerical stability. We check the shape of the training subset to confirm it matches what we expect, which tells us the data slicing was done correctly. We then do the same for the test subset, verifying its dimensions as well. By confirming both shapes, we ensure that the training and test datasets are correctly prepared for the next steps in the training process. We configure the backbone model to expect images that are 32 pixels high and 32 pixels wide, matching the size of CFAR10 images. We also set the number of output classes to 10, which corresponds to the 10 categories in the CFAR10 dataset. This ensures that the input images and the model's output layer are correctly aligned with the classification task. We use a simple sequential model in Keras to resize images so they are compatible with the pre-trained backbone. This model includes a resizing layer that converts all input images to 96 by 96 pixels. Matching these dimensions to what the backbone expects ensures the images are processed correctly and the model functions as intended. We apply a resizing layer to both the training and test images so that every image is adjusted to 96 by 96 pixels, matching the input size required by the pre-trained backbone model. Using the same resizing for both subsets keeps the image dimensions consistent. This step is essential to ensure compatibility with the model architecture and to make sure images are processed correctly during training and evaluation. We print the shape of the resized training data to confirm it matches what we expect before building the model. This quick check verifies that pre-processing steps like resizing were applied correctly. It also ensures the data has the proper dimensions and format required for the model's input. By doing this, we reduce the risk of errors later in the modeling process. We use a small pre-trained convolutional neural network, specifically MobileNet v2 from the Keras library, as our backbone model. Its input size is set to 96 by 96 pixels, with 3 color channels to match our resized images. We turn off the original fully connected classification layers so we can attach our own custom classification head. The model uses weights learned from the ImageNet dataset, allowing us to take advantage of features learned from a large collection of images. We begin by setting the model's backbone to be non-trainable, so its weights stay fixed during the initial training stage. This approach is common in transfer learning, where we want to use the pre-trained features of an existing model without changing them right away. After freezing the backbone, we print a confirmation to verify that it is indeed not being updated at this point in training. We build the model by first defining an input layer for images that are 96 by 96 pixels with 3 color channels. These inputs are passed through a pre-trained backbone network, which is kept frozen so its weights are not updated and this network extracts useful image features. We then apply global average pooling to compress the feature maps into a single feature vector, reducing parameters and helping to prevent overfitting. Finally, we add a dense layer with as many units as there are classes, using a softmax activation to output class probabilities and complete the classification head on top of the backbone. We build the full transfer learning model by combining the input layer, the pre-trained backbone, and the classification head into one model. The backbone processes the input images and extracts useful features learned from previous training. The classification head then uses these features to produce predictions for our task. This design lets us reuse powerful pre-trained features while training only the final classification part on our specific dataset. To begin the first stage of training, we compile the model by choosing key settings. We use the Atom optimizer with a learning rate of 1000, which offers a good balance between training speed and stability. The loss function is sparse categorical cross-entropy, appropriate for multi-class classification when the labels are integers. We also track accuracy as the main metric to see how often the model predicts the correct class during training. Training begins by updating only the classification head of the model using the resized training images and their labels. The model is trained for 2 epochs, meaning it passes over the entire dataset twice, and uses a batch size of 64, so weights are updated after every 64 samples. 20% of the training data is set aside for validation to track performance on unseen data during training. Progress messages are turned off to keep the console output clean while this process runs. After the first training stage, the model is evaluated on the test data to see how well it performs on unseen images. The evaluation function takes the resized test images and their labels as input and runs silently without printing detailed output. It computes the loss and accuracy on this test set and stores these values for later use. This step provides an initial measure of the model's performance after the first phase of training. We report the test accuracy after the first stage of training to show how well the model performs on unseen data at this early point. The accuracy value is rounded to 4 decimal places to keep the result clear and easy to read. This provides a concise, standardized metric for evaluating the model's initial performance. We start by making the entire backbone model trainable, so all layers could, in principle, be updated. Then, we immediately freeze the first 80 layers so they remain fixed during training. This lets us keep the useful pre-trained features learned in the early layers, while only fine-tuning the deeper layers. In this way, the model adapts to our specific task without losing the general representations captured at the beginning of the network. To find how many layers of the backbone model are trainable, we create a list that marks each layer as either trainable or not, then sum the true values in that list. We use a numerical library to efficiently perform this summation. The result is an integer that tells us how many layers are currently being updated during training. This count shows how much of the backbone is being fine-tuned at this stage. We recompile the model for fine-tuning by lowering the learning rate to 1 × 10⁻⁴, so the updates during training are more precise. We continue using the Atom optimizer because it works well with sparse gradients. The loss function remains sparse categorical cross-entropy, which is suitable for multi-class classification. We also track accuracy as the main metric to monitor how well the model is performing during training. We now train both the classification head and the selected backbone layers using the model's fit function on the resized training images and their labels. The training runs for 2 full passes over the dataset, known as 2 epochs. We use a batch size of 64, so the model updates its weights after processing 64 samples at a time. In addition, 20% of the training data is reserved for validation to monitor performance during training. The training output is kept minimal by turning off detailed progress messages. After the second stage of training, the model is evaluated using the test dataset. The evaluation function is applied to the resized test images and their labels to measure how well the model performs. It calculates both the loss and the accuracy on this unseen data. The process is run in silent mode, so it does not print detailed output to the console while evaluating. After the second stage of training, we report the test accuracy to evaluate how the model has improved. We round this accuracy to 4 decimal places to keep the result clear and easy to read. This rounded value gives a quick view of how much performance was gained by fine-tuning selected layers of the backbone model. The code compares the model's accuracy after the first and second training stages by subtracting the first accuracy from the second. This difference is called the accuracy gain and shows how much performance improved during fine-tuning. The value is rounded to 4 decimal places for clarity and then printed, giving a quick view of the benefit from the second training stage. This script shows a 2-stage training process using a small pre-trained convolutional neural network, MobileNet v2, on a reduced CIFAR10 dataset. It sets a fixed seed, checks for GPUs, loads and pre-processes the images to match the model's input, then first freezes the backbone, so only the classification head is trained, and evaluates test accuracy after 2 epochs. In the second stage, some backbone layers are unfrozen for fine-tuning with a lower learning rate, and the model is trained and evaluated again. The script reports the TensorFlow version, available GPUs, dataset shapes, the number of trainable backbone layers during fine-tuning, and the test accuracy after each stage, highlighting the accuracy gain from the first to the second stage. Gentle backbone learning rates. When you move from training only the new classification head to fine-tuning the entire model, the learning rate for the pre-trained backbone becomes very important. The backbone already encodes rich visual features from pre-training, and a learning rate that is too high can overwrite these useful weights and destroy valuable representations. Using a smaller, gentler learning rate lets the backbone adjust slowly, making careful updates instead of drastic changes. This cautious approach preserves the backbone's learned features while gradually aligning them with the new task. When fine-tuning a model, you should usually use a much smaller learning rate for the backbone than for the new classification head. The head is learning from scratch and can change quickly, while the backbone already has useful features and only needs small adjustments. This is especially important in settings like medical imaging, where the head must adapt to new labels, but the backbone should slowly refine its understanding of medical patterns. Using different learning rates in this way stabilizes training, protects valuable learned features, and improves generalization on small or differently distributed datasets. Adjusting the learning rate for the backbone affects how you schedule training, including when to unfreeze layers and how long each phase lasts. Using a small learning rate at first lets the optimizer make gentle updates that preserve the pre-trained features while adapting to the new task. As training progresses and performance stabilizes, you may reduce the learning rate further, so updates stay cautious near a performance plateau. This strategy is especially important in real-world tasks like quality inspection, where a gentle backbone learning rate helps prevent overfitting and improves reliable defect detection while still adapting to variations in the data. Python code, gentle backbone learning rates. This script demonstrates how to fine-tune a pre-trained convolutional neural network using gentle, staged training. It emphasizes using small, conservative learning rates for the backbone of the network. The goal is to adjust the pre-trained layers carefully, reducing the risk of destabilizing the model while still allowing effective adaptation to the new task. The line with the exclamation mark is a command to install TensorFlow version 2.20.0, ensuring the script uses the correct version for compatibility with the rest of the code. In this case, the line is commented out, which means the installation step is optional or has likely already been done in the current environment. As a result, the script assumes that the required TensorFlow version is already available and does not automatically reinstall it. To begin setting up TensorFlow training, we import a few key libraries. We bring in an operating system library for possible system interactions, even though it is not directly used here. We also import a random number library and a numerical computing library, both of which help us work with arrays and set random seeds for reproducible results. Finally, we import TensorFlow itself, which is the main tool we use to build and train machine learning models in this script. We begin by setting a seed value, such as 42, so that all random operations are repeatable each time the script runs. To do this properly, we set the seed for the random module, for NumPy's random number generator, and for TensorFlow's random operations. Using the same seed across these libraries keeps their random behavior consistent and ensures our experiments are reproducible. This line displays the version of TensorFlow currently in use. Checking the version helps you confirm that your environment matches the expected setup. It is important for compatibility, so your code behaves correctly. By verifying the version, you can avoid issues that come from using the wrong release of the library. The code uses a TensorFlow configuration function to list all physical devices of type GPU, and then counts how many are available. It prints this number so the user knows how many GPUs can be used for training. This helps the user understand the hardware resources that are accessible for running and scaling their model. We begin by loading the CFAR10 dataset using the Keras tools in TensorFlow. CFAR10 is a standard machine learning benchmark with 60,000 images grouped into 10 classes. The data is divided into 50,000 training images and 10,000 test images. This split lets us train the model on labeled examples and then evaluate how well it performs on new, unseen images, which helps measure how well the model generalizes. To quickly demonstrate the process, we work with a smaller subset of the training data. We choose 2,000 samples for training and 500 samples for testing. We then keep only the first 2,000 entries from the original training set. This reduced dataset makes experimentation and testing faster and more manageable. We reduce the dataset size by taking only the first 2,000 training labels so they match a smaller training set. We then select the first 500 test images and apply the same slicing to the test labels. This keeps the test images and labels aligned and consistent. Using this reduced set makes the data more manageable and allows for quicker demonstrations and testing. We first convert the training images to floating point values so that each pixel lies between 0 and 1 by dividing by 255. This normalization is important because it helps neural networks train more stably and efficiently. We apply the same normalization to the test images to keep the data consistent across training and evaluation. To prepare images for MobileNet v2, we use TensorFlow to create a resizing layer that sets each image to 160 by 160 pixels. We then apply this layer to all training images so they are automatically transformed to the required size. This resizing step is essential to ensure the images are compatible with the MobileNet v2 architecture. We now apply the same resizing step to the test images, using the previously defined resizing layer. This adjusts the test images so their dimensions match the input size required by the MobileNet v2 model. Keeping the input shape consistent between the training and test data is essential. It allows the model to process test images correctly and ensures that evaluation results are accurate and reliable. We check the shape of the resized training data to make sure it matches the expected dimensions before building the model. This confirms that the resizing worked correctly and that the data is in the right format for the neural network. We do the same for the resized test data to ensure it has the same structure as the training data. This consistency across training and test sets is important for reliable model performance. For the CFAR10 dataset, we set the number of target classes to 10 because it contains 10 distinct categories. This value determines how many outputs the neural network must produce. By matching the size of the output layer to the number of classes, we ensure the model can predict all possible categories in CFAR10. We load the MobileNet v2 model, a widely used convolutional neural network, and set its input size to 160 by 160 pixels with 3 color channels to match our images. We disable the original final classification layers because we will add our own custom layers for our specific task. The model's weights are initialized from training on the large ImageNet dataset, so we can take advantage of its pre-trained feature extraction for better performance. In this setup, the backbone of the model is initially frozen, meaning its weights are not updated during the first stage of training. This allows the training process to focus only on the new classification head so it can adapt to the specific task. By keeping the pre-trained backbone fixed, the model preserves the useful features it learned from the large original dataset, while the new head learns how to use those features for the current problem. We begin by defining an input layer for the neural network that matches our resized images, which are 160 by 160 pixels with 3 color channels. This layer is the entry point where image data flows into the model. We then apply the MobileNet v2 preprocessing function to these inputs, so the images are transformed into the format that MobileNet v2 expects. This preprocessing step ensures the data is consistent with the conditions under which MobileNet v2 was originally trained. The scaled input images are first passed through the pre-trained MobileNet v2 backbone, which extracts visual features using its fixed weights without further training. After these features are obtained, a global average pooling layer is applied. This layer compresses each feature map into a single value by taking its average, reducing the spatial dimensions. The resulting compact feature representation then serves as a summarized input for the following dense layers in the model. We first add a dense layer with 64 units and a ReLU activation to give the model more capacity and introduce nonlinearity, which helps it learn complex patterns. Then we add a second dense layer whose number of units matches the number of classes. This final layer uses a softmax activation to convert its outputs into probabilities for each class. The model then predicts by choosing the class with the highest probability. To build the complete model, we combine the pre-trained backbone with our custom classification head using the TensorFlow model class. We define the resized images as the model inputs and the outputs from the dense layers as the model outputs. This links the feature extractor and the classifier into one unified network. The result is a cohesive model that is ready to be trained for our classification task. We begin the first training stage by compiling the model with the Atom optimizer, using a relatively high learning rate of 1 times 10 to the negative 3, so the classification head can adapt quickly. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification tasks, such as CIFAR 10. During training, we also track accuracy as a key metric to monitor how well the model is learning to classify the images. We start training by updating only the classification head of the model. Using the resized training images and their labels, we train for 2 full passes over the data, with batches of 64 samples at a time. A fifth of the training data is held out for validation, so we can track performance on unseen examples during training. No progress messages are printed, and this phase allows the classification head to learn initial patterns while keeping the pre-trained backbone unchanged. Now we make the backbone of the model trainable again, allowing its previously frozen weights to be updated during training. This step is essential for fine-tuning because it lets the model adapt its pre-trained features to the new dataset. However, we typically adjust these weights gently, so we improve performance on the new task while still preserving the useful knowledge the model has already learned. We use a very small learning rate for the model's backbone, so we can fine-tune it gently without disrupting its pre-trained features. By keeping the learning rate as low as 1 times 10 to the negative 5, the weight updates stay minimal. This careful adjustment helps preserve the useful information the backbone has already learned, while still allowing it to adapt slightly to our specific dataset. We train the model using the Atom optimizer with a small learning rate that matches the gentle backbone setting, so the pre-trained features in the backbone are preserved during fine-tuning. For the loss, we use sparse categorical cross-entropy, which is appropriate for this kind of multi-class classification task. During training, we track accuracy as the main metric to evaluate how well the model is performing. We now fine-tune the entire model for a short time using a small learning rate on the backbone, so we do not disturb the pre-trained features too much. The training function is called on the resized images and their labels for 2 epochs, meaning the model sees the full dataset twice. A batch size of 64 controls how many samples are processed at once, and 20% of the training data is held out for validation to monitor performance. Training runs silently with no progress printed, focusing on gently refining the model rather than making large changes. After the staged fine-tuning, we evaluate the model using the resized test images and their labels. The data is processed in batches to handle the test set efficiently. The evaluation runs silently without printing progress information. This step computes the loss and accuracy on the test data, giving a final measure of how well the model has learned from training. We first report the final validation accuracy from the initial training stage, where only the classification head was trained with a higher learning rate, while the backbone remained frozen. This accuracy shows how well the head alone performs. We then report the final validation accuracy from the second stage, after fine-tuning the entire model, including the backbone, with a much smaller learning rate. Comparing these 2 accuracies lets us judge the impact of each stage and check that the gentle fine-tuning preserved the useful pre-trained features. At the end of training, the script reports the test accuracy of the gently fine-tuned model. This accuracy shows how well the model performs on new, unseen data after the staged training process. During this process, the backbone was updated with a small learning rate, so its pre-trained features were largely preserved. The final test accuracy therefore reflects the benefit of this careful adjustment strategy. This script shows how to fine-tune a pre-trained MobileNet v2 convolutional neural network on the CIFAR 10 dataset in 2 stages. After setting up a reproducible environment and preparing a small, normalized, and resized subset of images. It builds a model by freezing the pre-trained backbone and adding a new classification head. In the first stage, only this head is trained with a relatively high learning rate. Then the backbone is unfrozen, and the entire model is fine-tuned with a much smaller learning rate to preserve the useful pre-trained features. The script reports validation accuracy after each stage and final test accuracy, illustrating that careful, low learning rate fine-tuning helps adapt pre-trained models to new tasks without destroying what they have already learned. Overfitting monitoring strategies. When you fine-tune deeper layers of a pre-trained convolutional network, the risk of overfitting grows, so you must monitor it closely. Use a validation set that matches your real deployment conditions and track both validation accuracy and validation loss. Changes in loss often reveal overfitting earlier than accuracy does. For example, if training loss keeps decreasing while validation loss starts to rise, the model is likely memorizing instead of generalizing, and you may need to shorten fine-tuning or lower the learning rate. To understand how fine-tuning affects generalization, you should look beyond overall loss and accuracy and track class-specific metrics such as accuracy and sensitivity. When you change the model by unfreezing layers or adjusting the learning rate, you may see gains for common classes but not for rare ones, which can signal overfitting. In applications like wildlife conservation, this means the model might still perform poorly on rare species. Watching for these confusion patterns helps you detect bias and decide how to adjust your training strategy. When fine-tuning a model, use automated early stopping and checkpointing based on validation metrics, instead of a fixed number of training epochs. Let changes in validation loss guide decisions about when to stop, adjust learning rates, or revert to the best saved model. In safety-critical domains like autonomous driving, keep a separate test set focused on rare conditions to check real-world reliability. This helps you see whether fine-tuning truly improves robustness rather than just performance on the training data. Python code. Overfitting monitoring strategies. This script demonstrates how to monitor staged fine-tuning of a model. It uses a small convolutional neural network with transfer learning to adapt a pre-trained model to a new task. During training, it tracks validation loss to watch for signs of overfitting. When validation loss stops improving or starts to increase, it indicates the model may be learning noise instead of useful patterns. A line that begins with an exclamation mark is a command to install a specific version of TensorFlow, in this case version 2.20.0. This is done to make sure the script uses the correct library version, which is important for compatibility and for being able to reproduce results. The exclamation mark shows that the command is intended to be run in a Jupyter notebook or a similar environment where you can execute system commands directly from the notebook. We begin by importing several key tools for our work. The operating system module lets us interact with the system environment, and the random module allows us to generate random numbers, such as for shuffling data. We then import NumPy for efficient numerical computations with arrays and mathematical operations. Finally, we bring in TensorFlow, which we will use to build and train neural networks and to monitor overfitting in our machine learning models. We begin by setting a seed value of 42 so that any random operations in our code are reproducible. We apply this seed to the random library, to NumPy, and to TensorFlow so that all three use the same starting point for their random number generators. Using a consistent seed across these libraries ensures we get the same results each time we run the experiment. This reproducibility is important for debugging and for reliably comparing different runs of our models. We begin by printing the current TensorFlow version to understand exactly which setup the code is running in. This helps check compatibility, since different versions can change features or behavior. Knowing the version is especially important when debugging issues. It also makes it easier to share code with others and ensure they can reproduce the same results. The code uses TensorFlow to check whether a GPU is available by listing the physical devices on the system. Based on this check, it decides if the script will run on a GPU or fall back to using only the CPU. It then prints a message to inform you which hardware will be used. This helps you understand the computing resources available, which can have a major impact on model performance. This code uses TensorFlow's Keras tools to load the CIFAR-10 dataset, a standard benchmark for training image classification models. CIFAR-10 contains tens of thousands of small color images grouped into 10 categories. The data is divided into a larger training set and a smaller test set, so the model can learn from one portion and then be evaluated on separate, unseen images. This split helps measure how well the model generalizes beyond the data it was trained on. For a quick demonstration, we work with a smaller subset of the data instead of the full dataset. We limit the training set to 2,000 images with their labels and the test set to 500 images with their labels. By reducing the number of samples, the process runs faster while still letting us see how the model learns and performs. This approach is useful when we want to focus on understanding the workflow rather than achieving the best possible accuracy. We set aside a small portion of the test dataset to use as a validation set by taking the first few images and their labels. This validation set is not used for training, but instead for checking how well the model performs on data it has not seen before. By monitoring performance on this unseen validation data, we can detect and reduce overfitting during training. The code converts the training and validation images to floating point numbers and scales their pixel values to lie between 0 and 1. This normalization standardizes the input data, which makes the training process more stable and efficient. As a result, the neural network can converge more quickly and learn more effectively from the images. Before building the model, we first print the shapes of the training and validation datasets to verify that the data is correctly formatted. The training data shape shows the dimensions of the input images and their labels, confirming that they match the expected structure. We then check the validation data shape in the same way. This quick inspection ensures both datasets are properly prepared and ready to be used in the modeling process. We use a small pre-trained model called MobileNet V2 from TensorFlow as the backbone of our neural network. Its input is set to images that are 96 by 96 pixels with 3 color channels, which matches what this model expects. We turn off the final fully connected layers so we can later attach our own classification head. The model uses weights pre-trained on the ImageNet dataset, allowing us to reuse powerful features learned from a large and diverse collection of images. The code marks the base model as not trainable, which freezes all layers of the pre-trained backbone, so their weights are not updated at first. This means only the newly added classifier head is trained on the current task. By doing this, the model reuses the useful features learned during pre-training, while reducing the risk of overfitting the backbone to the new dataset too early. It is a way to focus learning on the task-specific layers before fine-tuning the entire network. We define the model's input layer to accept images that are 32 by 32 pixels with 3 color channels. These images are then resized to 96 by 96 pixels, because the pre-trained MobileNet V2 model requires that input size. After resizing, we apply the MobileNet V2 preprocessing function, which scales the pixel values into the range expected by the model. This sequence of steps ensures that all input images are correctly formatted for the pre-trained network. We begin by sending the pre-processed images through the MobileNet V2 backbone, which acts as the base model and extracts high-level features while its weights remain fixed in inference mode. Then we apply global average pooling to these feature maps, collapsing their spatial dimensions by averaging each map into a single value. This produces one compact feature vector that summarizes the entire image. Finally, this pooled vector is passed to the classifier head, which uses these summarized features to make the final predictions. To adapt the model for the CIFAR-10 dataset, we add a small classifier head on top of the existing network. This head is a dense layer with 10 units, one for each CIFAR-10 class, and it uses the softmax activation function to produce class probabilities that sum to 1. We then define the final model by connecting the original input layer through the network to this new classifier head, so the model can output a probability distribution over the 10 classes for each input image. We begin by compiling the model for its initial training phase using the Atom optimizer, which is effective for problems with sparse gradients. The learning rate is set to 0.001 to promote stable and reliable convergence. For the loss function, we use sparse categorical cross-entropy, which is appropriate for multi-class classification tasks like CIFAR-10, where the labels are integer encoded. We also track accuracy as a metric to monitor how well the model is learning during training. We use an early stopping callback to monitor training by tracking the validation loss, which measures error on the validation set. If this loss does not improve for 2 training epochs in a row, the callback stops the training process to prevent unnecessary updates. It also restores the model to the best set of weights seen during training, so we keep the most effective version of the model. We start by training only the classifier head of the model, using the training images and their labels. The model goes through the entire training set up to 3 times, processing the data in batches of 64 examples. During training, we also check performance on a separate validation set, but we do not print detailed logs. An early stopping mechanism monitors the validation loss and stops training if it does not improve for 2 epochs in a row, then restores the best model weights found so far. The code looks through the recorded validation losses from the first training stage and finds the smallest value. It then prints this best validation loss, rounded to 4 decimal places. This value summarizes how well the model performed during the initial phase of training and makes it easier to compare performance across stages. To enable fine-tuning, we unfreeze the top part of the backbone model so it can be updated during training. Specifically, we take the last 20 layers of the base model and mark them as trainable. This means their weights will be adjusted when we train on our dataset. By allowing these upper layers to adapt, we can better tailor the pre-trained features to our specific task and often improve overall model performance. We recompile the model to lower the learning rate, which is important for stable fine-tuning. The optimizer remains Atom, but its learning rate is reduced to 1/10 of the previous value to avoid large, destabilizing weight updates. We keep using sparse categorical cross-entropy as the loss function because it fits our multi-class classification task. Accuracy is still tracked as the main metric, so we can monitor how well the model is learning and performing. In the second training stage, we use an early stopping callback that watches the validation loss to help prevent overfitting. If the validation loss does not improve for 2 epochs in a row, training stops before completing all planned epochs. The callback also restores the model weights to the best version seen during training, so we keep the most effective model configuration. In the second stage, we train the model using the training data and their labels. The model passes through the entire dataset 5 times, and it updates its weights after processing groups of 64 samples at a time. We use separate validation data to track how well the model is performing during training. The training runs silently without detailed logs, and an early stopping mechanism halts the process if the validation loss stops improving, which helps reduce overfitting. We evaluate the second training stage by finding the lowest validation loss recorded during that phase. This minimum value represents the best performance the model achieved while being fine-tuned. We then print this best validation loss, rounded to 4 decimal places, to make it easy to read and compare. This gives us a clear benchmark for judging how the fine-tuned model compares to the initial training stage. The code checks whether fine-tuning actually improved the model's ability to generalize by comparing the best validation loss from the second training stage to the best validation loss from the first stage. If the second stage achieves a lower validation loss, it concludes that fine-tuning was successful and advises keeping the updated weights. If the validation loss does not improve, it determines that fine-tuning did not help and recommends reverting to the earlier checkpoint. In this way, the decision to keep or discard the new weights is based directly on validation performance. We generate a brief summary of the training monitoring process. First, we state that this is a monitoring summary, then report how many epochs were completed in the first training stage by checking the length of its loss history. We do the same for the second stage to show how many epochs it ran. Finally, we present a decision message that explains whether fine-tuning improved the model, based on comparing the validation loss from the 2 stages. We evaluate the final model using the validation set to measure how well it performs. An evaluation function runs on the validation data and labels and returns 2 key metrics: validation loss and accuracy. We then store these values and print them, rounded to 4 decimal places, to give a clear and concise summary of the model's performance on the validation data. This script shows a staged fine-tuning process using a small convolutional neural network with transfer learning to track and control overfitting. It prepares a reproducible setup, selects a GPU if available, and trains on a normalized subset of the CIFAR10 dataset. A MobileNet v2 backbone is used with a custom classifier head, and at first, only the classifier head is trained, with early stopping based on validation loss. Then the top layers of the backbone are unfrozen and fine-tuned, again with early stopping, and the validation losses from both stages are compared to see if fine-tuning improved generalization. If the second stage achieves lower validation loss, fine-tuning is considered beneficial, and the final model is evaluated on the validation set to report loss and accuracy, illustrating the impact of fine-tuning on performance. In this lecture, you learned to load and adapt pre-trained CNN backbones from tf.keras.applications for new classification tasks, configure layer freezing and unfreezing strategies to balance feature reuse and task-specific learning, and implement a staged training schedule for fine-tuning and evaluate its impact on performance. In the next module, Module 7, we will go over NLP with TensorFlow.
Thank you for your attention. See you all in the next lecture.